All right, so actually for this chapter 10, I haven't gone over the slides at all. So let's quickly go over the slides. So I used the book, but let's see whether I have missed something not in our slides that I have on our course web page here, accessible from my website. So if you're looking at these lecture slides too, for chi-square test, we haven't gone over the lecture slides. But most of the things is repetition of what we have covered everything, but let's quickly go over them. Chi-square distribution, the section 9.5 that we skipped, it was the inference of variance that we have skipped. So it's all about how we model variance, in which these values are the difference from something, the squared differences from mean, just like the difference between our expected and observed values here. The variance is always positive, okay? Distribution starts at 0, it's always non-negative. And that's chi-square distribution. When we have independent, random independent data points, and they are normal with the distribution of this, when the chi-square with n-1 degree, this distribution of sample variance is chi-square. So we don't need to know these details. We have skipped that section. And you don't need to know this PDF of chi-square, but just there are some relationship of chi-square with other distributions. Chi-square is a special case of gamma distribution where alpha value of the gamma is degrees of freedom divided by 2, and alpha and lambda is 1 over 2. So for a value of lambda 1 over 2 and alpha degrees of freedom divided by 2, chi-square is that same distribution. So it's not a completely new distribution. Gamma, if you remember, it was a summation of exponentials, which were waiting times, which were always positive. So chi-square therefore starts at 0, it's always positive. So that's why it looked like chi-square with 2 degrees of freedom is exponential 1 over 2. When I looked at this figure and when I solved that, oh, it looks like exponential. So I wasn't wrong actually. For 2 degrees of freedom, chi-square with 2 degrees of freedom is going to be gamma 1 over 2. So it will be exponential with lambda is 1 over 2. And it has this expectation and variance, and we have covered this history about chi-square. We have seen this different chi-square shapes for different degrees of freedom. And yeah, we have went over this formula, what we can use chi-square test for. It's always a right tail test. Here, each category should have an expected count of at least 5. That's another thing. So testing against a specific distribution, we have covered this. This was the example, the Faraday example we have covered. And testing against the family of distribution, the only difference from the first case is the degrees of freedom decreases by the number of parameters that you estimate. So here it says we may use maximum likelihood estimator. So to answer your previous question, Khan, so we can use other estimators too. Okay, so maximum likelihood is not a hard rule. This transmission errors, we also covered this. That was again an example from the book where lambda was 1.55. So that's the same example. And testing independence, the spam email thing example, I think is the same. Yeah, we have also covered this one. So yeah, we have covered every one of these slides. So this officially concludes our discussion on chapter 10. Now, we are going to talk about regression. And this is this may actually deserve more time that we are going to cover in this course. But since this is an introductory course for statistics and probability and statistics, you're not going to cover everything in detail. And the reason that we touch up on this topic of regression is to tell you what regression is about, how it tries to it can be used to predict certain things, some numerical values, if we have some reporter, some variables that we can measure, and we use it to predict some another variable. So that's if that variable takes some numerical quantitative values and we try to estimate what it is, like estimating what the population of the world be in 2030, or estimation of an house price based on some features of an house. These are all regression problems, trying to estimate some numerical problem. And there are different, we are trying to basically learn a function. Since we're trying to predict some numerical value, the problem of regression is to learn a function that is a function of these computable observed values, observed features of something. And by using that, this function is going to result, the range of this function will be that thing that we try to predict, whether it's the population, whether it's the house prices, or the value of a stock in stock market. So things like that fall into the problem of regression. Least squares estimation for regression is there are many different techniques for regression, and one of them is least squares. It tries to, based on some training data, based on we have a sample here, and our goal will be to learn a function which minimizes the error between the sample's actual value. So this is, as I said, this is like a training set. Imagine we have like 10 house prices, 10 houses in which we compute certain features of those houses. And imagine we also know their actual prices. So assuming that we don't know the prices, when we apply our learned function on them, it will predict the house price. So least squares tries to minimize the difference between the actual house prices and the prices that are predicted by our function. So it tries to find a function in which the differences between our training data and the predicted values are going to be as small as possible. The square differences, the square deviation between the actual prices and the predicted prices are minimum with respect to a given training set. So that's what least squares is in general. And when the function, if the function that we try to learn is just a linear function of those input features, that's called linear regression. You may try to learn different functions, quadratic function. There's, for example, logistic regression, which uses a logistic function, which is not non-linear. But again, in this course, our goal will be to learn linear regression, the simplest form, linear regression, and we will do that by using least squares linear regression. So if I want to show you how the problem looks like, it's something like this. You have some variable, a random variable that you observe, and another random variable, y. So here, in general, in regression problem, you may have multiple things, multiple variables that you observe. You may have x1, x2, x3. It may be multivariate regression. In the simplest case, univariate regression, we are going to have some value that we compute. For example, these may be, as I said, a certain value of the house. For example, the squared area of the house. Based on that, for example, what is its price? So each of these dots will be corresponding to some house, some particular house. Okay. Now, here in our sample, maybe there are 7 houses, and their y values correspond to their actual prices. So in our training data, we have their actual squared area, and we also have their prices. Now, our goal will be to learn a function in which we will be able to try to predict y so it will be a function of these x. Learn a function which will take this x as input and try to predict y out. So we may have there may be a function. It's possible to have a polynomial function, for example, which will be something like this. Look at this. We can have by using, for example, splines or a higher order functions. For example, I have seven points here, right? 7 points in my training data set. You can have a function like this. Y is equal to ax to the power 6 plus bx to the power 5 plus cx to the power 4 plus, you get the idea, plus, so ABC, D, E, F, G, seven unknowns. So dx to the 3, let me write all of them, ex to the 4, 2, and fx, yeah, ex, e to x to the power 2, fx plus g. So I have 7 unknowns here, a, b, c, d, e, f, g, 7 unknowns. I have 7 points here. I can actually have 7 equations, 7 unknowns from here for each values of x. Each value of x here, I will just plug it in here. It will give me an equation. Since I also know their y values, it will give me 7 equations, 7 unknowns. And you can have a very high order polynomial like this, sixth order a polynomial of 6th degree, in which you will be able to, since you solve these equations by making all of these equalities satisfied, which means that the squared errors, which are called residuals, the difference of the actual y. So if this is your function, if you find these a, b, c, d, g, all these 7 values, these constants, you will have a function something like this. Maybe y minus 0.2 x to the power 6 plus 0.3 x to the power 5. So you will have some function like this after you find what those a, b, c, d's are. And for every value of x in your training set, you will exactly find their value. So this seems like a really good model, right? That with 0 prediction error, we will be predicting all the 7 values in my data set perfect. But it's, in terms of machine learning, I mean, models go, this is actually a very bad model. Because it will probably, for example, if there's a new data set, I mean, we learn a model by just looking at the training data set. In general, we call this detailed model with many parameters which pass through all of them. This may be a very accurate model on the training set, but its generalization performance will be very, very, very bad. Look at this curve. The curve goes like this here. If I have a house that is with area here, its prediction will be somewhere here, right? Which is way off than the actual value. If I have a house that is like this, the predicted value will be here, and it's way off. So it fitted perfectly on our training data set, but here we call such a fitting overfitting. So we don't want to overfit the data set, because if you want to minimize the error here to make it 0 and have a higher order, more detailed model like this, it's so detailed a model that it cannot generalize to cases that are not seen because it overfit our data. Now, the basic rule of thumb in machine learning is that use as simple models as possible. Use a simple model as possible, because in this case, simple models will have a better generalization performance. But sometimes simple models make many errors. Maybe the data itself is distributed in such a way that a simple model like a line, a linear model, will not fit, and it will not have a good generalization performance either. So based on the distribution of the data, sometimes we may need to model the relationship between x and y by using higher order functions like this. But if you can use a simple model, use that model as much as possible. And here in this course, we're going to see the simplest model that we can have on univariate regression, which is linear regression, which means that basically if you have these values here, your goal will be to find a function which is something like this, ax plus b, which is a line. Okay, the order of, it's a polynomial of degree 1, which means that it's a line. We are going to find a line, if this is x and this is y, we are going to have a model which is basically a line. Our goal, the outcome out of this chapter will be how we can find this a and b, these constants in this line will tell you your model basically. How do you find a and b given some training data? Now, which line do you think is the best model for this? For example, is this line a good prediction for these data? So intuitively, what you would want to do here, is this line a good prediction? You would want a line that pass as close as possible to all of these points, right? And this line, the third line, I think is a better model for our training data set compared to line 1 and line 2. And why is that? Because it passes as close as possible to all the points. So how can we find this line? That's what we call least squares regression. Here our goal will be the difference between the points on the line at that x will be, so this will be the predicted value at that value of x. For this value of x on the x line, the value on the line will be the one that is predicted by our function, right? And if this is the actual value, the difference between these two, so these will be our differences, residuals, and we are going to take the squares of these and we'll try to find a line that minimizes. So we are going to first write this function as a general function. What are the differences between our data points and the predicted ones? For example, this is the predicted one. So ax plus b is the predicted one. And the difference from the observed one, if this is xi, yi is, we also have the observed y value. We are going to look at this difference and take the square of this and sum them up. This will be our summed square, summed residuals, that be differences from the model and the observed counts. And we will take the derivative of this. Our goal will be to minimize this function. And in order to minimize this function, there are two unknowns, a and b. Write this function, we are going to take the derivative with respect to a, then take the derivative with respect to b, solve that. It will give you two and set them to 0 to get those minimize those functions, and you will have two equations, two unknowns, and this is how our least square solution is going to give us what a and b is with respect to xi's and yi's. So that's this entire summary of what we are going to be seeing in this section 11.1 in this chapter. Okay, so if we go now systematically, that's a very good question, Furkan. So what if we have outliers? For example, if we have an outlier here, that would make since if you look at these residuals, all of them are treated equally, right? I mean, a large residual here, you will also try to minimize that too, because you will have your line with a lower slope. If you have an outlier point here, this will cause a big residual, and you would not want that. Your error is going to be very large. This will cause your prediction to go a little bit lower like this. Only because of this outlier, you will be making you will be increasing your errors for the other points. So that's a very good point. So if you want to increase the accuracy of our model, we need to do something about outliers. I would suggest if you observe in univariate regression, finding outliers may not be very difficult. I mean, you first visualize your data. Maybe if you see some outliers in your data points, you may just remove them manually, or based on the values of x and y, you may also ignore certain if, for example, if in this model, if you look at individual residuals, so if each of you can compute the individual residuals as a single number, right, all these squared residuals, and you may take a look at their average and how certain individual residuals are different from the overall residuals. For example, if all of them are like 1 point, the distance of each of these points are almost equal to each other between 1 and 2, but there are 2 points in which the residuals are like 10, 15. If after you do this, if you see that, that will you may get rid of those outliers. Exactly. They will manipulate the line. That's a very good point. Outliers will cause you to model, have this linear regression, an incorrect model. So removal of outliers is one thing you need to do. That's actually in many machine learning tasks, outliers are a problem. So therefore you need to have as a pre-processing step in your data set, if there are outliers, it would be really good to remove them first before you try to find a good model for your data. So yeah, thanks for pointing that out. And in general, regression could be done on many variables. So this is a multivariate regression. You may be measuring multiple things about the house, not just the squared area, the area of the house. It may be, for example, its location, its age, the age of the house, its location, whether it has certain features or not, whether it has a swimming pool, how many rooms does it have. So all these things may be the things that we measure about a house, and why may be the price of the house, for example. We may try to predict it based on these multiple variables. Here, the y in statistical terms, this y, the value that we predict, the quantity that we want to predict, is called the response or dependent variable. It's dependent on these other things. If it was independent of x, all these x's, if y was independent of these x's, it means that it will be impossible to predict y, right? Hence this name, that dependent variable, that name is an intuitive, has an intuitive meaning. Sometimes it's also called the response variable, dependent variable. And these x's are usually, they're called predictors, and they're sometimes called independent variables. But they may be, there may be correlations in between them. If that's the case, we may need to remove certain features. We may decrease the dimensionality if there is a lot of correlation between certain pairs of predictors. But usually these are called predictors, and this is called the response. And this is in general a difficult problem. There are many methods. If you take a machine learning course, I'm sure in that course you will spend 1 or 2 full weeks on this multivariate regression, and learn maybe a month to learn different methods to perform this regression. Usually when this another thing in machine learning is that when this response variable is not numerical but categorical, sometimes it's called classification problem. So if somebody asks you what is the difference between classification and regression, you may answer them all like this. I mean, in classification is also like regression, but why in that case becomes a class, a category of something. We are trying to classify, for example, whether given a painting, to classify what it's automatically whether it's impressionist painting, whether it's a classical area painting, or trying to automatically find the artist who did the painting. The number of artists in your set, they become categorical variables, and this becomes a classification problem in which in that case, that y will not be some numerical value, but it will be a category, a class. If we try to predict this given the features, that's the classical classification problem in machine learning. But that if that y is some quantitative numerical value, like the price of a house, or the population of the world in 2030, if it becomes a numerical value, in general, that's called a regression problem. And the linear regression is the simplest case, where we have the simplest model. So the function that, in general, we learn a function of x's to predict this y, that function g. If that function g is a linear combination of your predictors, like this, it's called linear regression. That linear regression, although it's a very simple function, you don't just treat it as a worst case to do regression. Actually, being simple, as I said, sometimes it's a desirable thing to be simple, because it will have better generalization performance. It will have less overfitting. You will not overfit your data with a linear model. Sometimes still linear models are used in certain machine learning problems. So it's not something bad. Being simple is not always bad. As I said, it avoids overfitting your data. And sometimes really the relationship between many features and some respondent variable may be linear, or maybe very close to linear. So that's not a bad model. So we are going to see here linear regression in this course, and we are going to see its simplest form, in which these independent variables, the predictors, will be just one variable, just one x. Excuse me. So it's going to be a single variable that's called univariate, not multivariate, univariate regression. Yeah, univariate linear regression, in which this function will simply be so it will be here, this function, you can also see what is the expected value of y given that x is equal to this value. And it will be a linear function like this. As I said, a plus bx, I wrote that. These are called beta 0 and beta 1, these two constants in the book. And the intercept b0 is the value of this function when your predictor is equal to 0. The actual semantics of beta 0 may not be meaningful, because in most of the cases, x never can be equal to 0 in reality. For example, in terms of house prices, do you have any house with area 0 square meters? It's not possible, right? This is what the meaning of beta 0 is. It's the intercept of this line, and so it's a simple y is equal to, like an y is equal to mx plus b type of equation, where b is your intercept and m is the slope of the line. Here beta 1 is the slope of our line, which shows actually how a unit increase, the slope of a line, basically tells us a unit increase in x, how much the response variable changes with a unit increase in x. And this is true for any value of x, so which means that the slope of the line is constant among the along the line. This is a constant value for all values of x. That's why it's a line, okay? A constant difference, unit difference, that's our slope. How much your respondent variable changes with a unit increase in x, that's what beta 1 shows. Here is an example that shows the difference between linear versus nonlinear regression. In linear regression, we try to fit the data points with a line. So this example is about world population. If we have the census data, the population data for the world between 1950 and all the way to 2010, as you can see, they're mostly linear. After you plot this data, the hollowed squares, circles, are your the training data. These are predictions for 2015 and 2020. I think they are really accurate. Since we have already passed 2020, we can check whether these predictions are actually true or not. And if you look at the house area in square feet with respect to sale prices in $1,000, we see all the training data is all over the place. We can still try to fit a line here, but the general trend of these points, training points, may look more like a non-linear function like this, and therefore you may choose to use a non-linear regression to do this model. So visualizing your data is really important, but such kind of a visualization may be difficult if you're not doing univariate regression. If you have a lot of dimensions, a lot of predictors, you may maybe try to view each of them separately first and try to see whether there are correlated linear or non-linear relationship between them. Now, the method of least squares, as I told you in my example, is these are called residuals, the difference between the predicted value that are on the line and the actual y value of those. Our goal will be, so if this is our x1, y1 values, our training data, our sample that is given to us, our goal will be to fit a line, to draw a line that passes as close as possible to these points. Again, assuming each of these points will have equal importance. There may be different variations of linear regression in which these points will have different weights. Okay, we may give them different weights when we are computing this based on whether they're outliers or not, or based on their x values. The difference we may want to have, we may want to make less prediction error, for example, when we are doing the prediction for a larger house. It may be okay if you're for a smaller house, if you make errors, you may tolerate it more. If you, for example, if semantically you have something like that, for a smaller house, I'm okay with making errors, but for a larger house, that's big money, I don't want to make errors. In that case, your linear regression actually may be modified to give more weight based on the x value of your house. Okay, so it is possible, but in the most simplistic general form, all these data points in our sample, they have equal importance. We find the residuals with equal weight. Here the difference between y1 and y1 hat, y2 and y2 hat. These hat ones are the ones that would be predicted if we use this function, g hat function, as our predictor. And here, these are the actual points. As you can see, that are, as given here, they become our residuals. And our goal is to minimize these residuals. Find gx in which these residuals is going to be as small as possible. So it's not possible to make them 0, as you can see. Since we have 5 points here, we cannot draw a line that passes through all 5 of them. It's not possible. They're not collinear. Therefore, there is no such line as possible. So we're bound to make some errors. We're bound to have non-zero residuals. And our goal will be to minimize that. So if we write those residuals, the difference between them, the squared residuals here, it becomes this. If we write what yi hat is in terms of this beta 0 and beta 1, this is our predictor function. As you can see, there are 2 unknowns here. Actually, this will be like there are a lot of equations. The number of equations we have here is n. So it's actually an overdetermined function. There is no, which means that may not be possible to find a single beta 0 and beta 1 that satisfy all these equations. Therefore, our goal will be to minimize this. So this is our function that shows the residuals. Take the partial derivatives of this function with respect to beta 0 and beta 1, set it to 0. That's why that's the place where we are going to attain its smallest value. These derivatives, after we take the derivatives and set them to 0, they become our two equations to find beta 0 and beta 1. Okay, so these are called normal equations, and the method of least squares. You're not responsible for the details of this derivation of how beta 0 and beta 1 is found, but if we, by just simple mathematics, we just try to solve these equations. Two unknowns, beta 0 then becomes equal to this value, y hat minus beta 1. So here beta 0, we find it with respect to beta 1. And if we substitute beta 0 in the second normal equation, we get ourselves a single equation here in which we see some similar looking terms. So here, this is the equation. Beta 1 is going to be equal to Sxy. If you write what beta 1 is going to be equal, this is going to be equal to Sxy divided by Sxx. These are like, this looks like the denominator. There's a reason why we call this Sxx, because it's like the numerator when we try to estimate sample variance of the single random variable xi's. This would be what we would look at, what we would have in the numerator, right? I mean, if you divide this by 1 over n minus 1, that's the sample variance for x. And if you see what this is, the summation of xi minus x bar, y minus y bar, this looks like the numerator in the covariance. I mean, if you were to estimate the covariance between these two variables, this is what we would have in the numerator. So that's why this is like we can also call this as sum of cross products, sum of squares, but these are here. We first need to conduct, so the general rule is we first find the average of x values, find the average value of y values. Your Sxx is the difference of all those individual x's from your x averages squared. You sum them up. That's your Sxx. Sxy is your, again, differences from your xi, and in which this multiplication may be a negative value. It's not necessarily positive, because one may be positive, the other may be negative, depending on what you have here. So this looks like some non-normalized covariance value here. So as an algorithm, if you look at the step-by-step algorithm, the first step, we compute these. Then we compute the Sxx value, which is the difference of all those individual x values from the sample mean squared, sum them up. We compute this Sxy2 by multiplying the differences of, for each I have m points in my sample. For each of those points, I take the difference from its mean on x, the difference of the same points y value against this average y value. I multiply them. As I said, this Sxy can be a negative value here, depending on how they are positively or negatively, like whether x and y is positively or negatively correlated. And our B1, which we call beta 1 hat, our least squares estimate for our linear regression line, would then simply be Sxy, this one, divided by Sxx will be our slope, and our intercept then will be this y hat minus b1 x bar. So if you look at this world population example, 11.3, let's go. Let's go to chapter 11. And again, since the final exam is going to be open book, you don't need to memorize any of these formulas. You'll be free to refer to these slides or the book to apply these if you're asked this as a question in the final exam. So you don't need to memorize them. Just know that they look like, as you can see, variance and covariance here. And if you look at this world population example, 11.3, this is house prices, method of least squares, yeah, linear regression, and 11.3 is somewhere here. Yeah. In the example, if we, the average, the x values are our years. So the average, it was The world population data was collected between 1950 and 2010. So for 60 years, the average year was 1980 here, as you can see. And the average population in those 60 years is, if you take the average of those Ys, it's 4, 4.5 billion. So I think this is like in millions, right? Then you compute SXX as the difference of all of these years from one the X bar, which gets you this. SXY again is going to be a multiplication of these with the difference from the Y bar, which is, since world population is positively correlated with year, you will, I assume, all get positive values here, which is going to be this large number. Then after you obtain this SXX and SXY, you also, it's simple matter. Also, you have X bar and Y by here. The slope becomes 74.1, and the intercept becomes some negative number. So that's actually, this intercept being negative doesn't make sense, right? If you were to predict what is the population in year 0, it would be some negative number, which doesn't make sense. So our prediction actually, based on collected data in linear regression, this doesn't predict the world population at year 0 correctly, but based on the data we have, it may be accurate prediction for the years coming up ahead. So this is the estimated line, with intercept being a very large negative number and with slope 74.1. If you apply this for, and you put it in terms of X here, 2015 and 2020, to predict the population, it will give you 7.1 billion people and 7.5 billion people in 2020, which is not very far away. I think they're close to 8 billion these days, but yeah, it's not a bad prediction. So regression and correlation coefficients, all these, since the formula of SXX and SY are really similar to, I mean, they're like the numerators in variance and covariance. So this regression is actually has a relation to covariance between two variables when we are doing regression. This was the correlation coefficient, if you remember, from chapter 2 or chapter 3. It was a normalized covariance by the standard deviation of these variables, and it was always between -1 and 1. If two variables are really highly negatively correlated, this correlation coefficient was -1, and it was 1 if they're positively correlated. And if you look at the sample covariance between X and Y, as I said, this is divided by n-1. In the numerator, we have exactly SXY here. And the sample correlation coefficient here, which with this row here, if we compute this from our sample, it will be sample covariance divided by sample variance of X and Y. Since sample standard deviation, Sx and Sy, these are sample standard deviations, unbiased estimator for our sample standard deviations. If we put all of these together, we see that, I mean, we already knew that the regression slope was Sxy divided by Sxx, as given by this formula. It is also very similar to, I mean, these n-1s, they're going to cancel out each other in this Sx, Sy. We have square root of n-1 multiplied by square root of n-1. We have n-1 here at 2 in Sxy, so they cancel out each other, and it turns out that we have the same thing here. It's, if you know the correlation coefficient, the slope becomes actually correlation coefficient. I mean, if you look at this, it will be correlation coefficient multiplied by Sy divided by Sx. So this is how covariance correlation coefficient is related to your regression slope, and it makes sense, right? I mean, if they are positively correlated, if they're exactly correlated, the slope is going to be 1. Depending on if their standard deviation is also equal, the slope we are going to have is going to be 1. the standard deviation is different. The slope is going to reflect the difference in their standard deviations too. So this is just a side note about how linear regression slope in univariate regression is related to covariance. I talked about overfitting a model. As I said, when we have these data points, we can have very complicated functions that pass through all of them. And if you look at these complicated functions, the residuals in all of them is zero. It perfectly matches the training data, but each of them make different predictions as to how it's going to behave for different values of x that we don't have in the training data. So we don't want overfitting like this. In most of the cases, a most simplest model, like a line, a linear prediction on the same data, is going to give us good results. Okay, so here is how covariance and regression and correlation is related. This is the same discussion in the book and the same discussion on being not, in order to not overfit data, a linear model is a good generalized model that does not overfit data. That's why we may first try a linear model on our data when we try to do regression. Okay, so this one also concludes chapter 11. We are right on schedule. So we have 3 weeks left. We are going to start chapter 5 next week, Monte Carlo simulation, in which you're going to have your last assignment is going to be a small program that does Monte Carlo simulation. And by the way, the deadline of your third assignment is extended for 3 days, so you will be able to submit it until Wednesday midnight. And after we finish chapter 5, you will have your fourth assignment, which will be this small program to conduct Monte Carlo simulation. All right, so